Okay, so this is going to be the first lecture on Riemann integral, and we are going to discuss Riemann integral as a topic of BA BSc mathematics. Okay. We are going to just go conceptually and systematically to understand what a Riemann integral is basically. Okay, so let us come straight to the point. Riemann integral. Clear? Riemann integral. So before understanding Riemann integral, let us first understand the concept behind the structure of Riemann integral. Then we will be moving on to what basic things we need to understand or construct the concept of Riemann integration. So Riemann integral basically deals with what we have read as definite integration. Okay, what we have read as definite integration, or definite integration as the area under curve. Okay, we in the +2 level we have read these things. So for example, you have a curve like this, let's say. So so a few concepts we had learned during indefinite integration in the +2 level, such that the concept of definite integration as the limit of sum, right? So what is the basic thing which we do to take the area under the curve, a curve like this? So what we can basically do is we can construct rectangles, like this, okay, so on and so forth, like this, okay, and we take the area of each such rectangle, and the total area of such rectangles approximately equal the area under the curve. If we take the breadth of the rectangles very small, clear, if they take the thickness of the rectangles very small, they approximately equal the area under the curve, right? So this concept of area under the curve of a given curve, using the concept of area, finding the area of rectangles, is what we use to understand Riemann integral, right? What we basically do is under Riemann integral, if we take the graphical understanding, so suppose you have a curve like this, right? So here we can form rectangles of two types basically. One which covers the area from below it, okay, for example rectangles of this type, right, and one which covers the area from above it. It's kind of bounds the curve from the above of it, right? For example, suppose we say rectangles like this, okay, rectangles of something like this sort, okay. So 1 minute guys, 1 minute. So suppose then we have like this, let's say, okay, then like this, okay, we take it from here, sorry, there's a little bit of mistake, let's say let's take it like this. Okay, suppose you take rectangles like this, okay, so these rectangles, they kind of cover the curve from the above of it, right? They kind of cover the curve from the above it, and in this case the curve covers the rectangles from above, right? So basically, now see, areas of this rectangles will also approximately give you the area of the curve, Okay, and the areas of this rectangle will also give you the approximate area of the curve, given that these rectangles are covered by the graph or the curve given, and these rectangles cover the curve given, and if the total sum of the total sum rather if the if the total sum of these areas of these rectangles and the total sum of the areas of these rectangles, okay, equal each other, then we can say that the area under the curve is basically given by the area of these rectangles, because the area of these rectangles and the area of these rectangles can equal each other only if the area of these rectangles give you the area under the curve, right? So this is the kind of the backbone of Riemann integral. Clear? To understand Riemann integral, the first thing which we need to understand is the concept of partitions of a given set. Partitions. Okay, what are partitions basically? So for some given interval, let's say, okay, for some given interval I, a comma b, closed interval, okay, so this is a for some given I where I is finite and closed I is finite and closed. Clear? So then by partition P of I, we mean a finitely ordered set. Okay, we mean a finitely ordered set P equals to elements start with the with the starting point of the given interval, and let us take it as x0, then we have x1, then we have x2, and so on, and ends with the end of the given interval, such that a equals to x0 is less than x1, which is less than x2, and this order keeps going till the value xn. Clear? Given. Now these points, what they do is they basically break the given interval into n number of sub intervals. Clear? These elements of the partition which we have taken as P, these points break the given interval I into n sub intervals. And why do we need these sub intervals? In very simple sense, we need these sub intervals to construct the rectangles whose area we are going to calculate, right, to approximate the total area of the rectangle to get the to approximate the area under the curve by calculating the total area of the n rectangles which can be formed using these n sub intervals. Clear? Got it? Got it. For example, we have n points taken here, and so they can form sub intervals of the form, say I1 is the sub interval x0 to x1, similarly I2 is the sub interval x1 to x2, and so on till In, which is the sub interval xn minus 1 to xn. So in a very generalized way, IR can be given as xr minus 1 to xr, this closed interval. Okay, is it clear? Is it clear? So we can form n such sub intervals using the elements of the partition, and these sub intervals will basically be required to construct the rectangles which we are going to need to approximate the area under the curve or find the definite integral of the given curve within this given interval. Clear? Clear? Okay. Now what do we, let us take an example. So suppose we have an interval 1, 3, let's say. Okay. So, and we take P as, let's say 1 by 2, 2, 2.5 and 3. Clear? Clear? So basically what are the partitions we have, what are the sub intervals which we are going to get using this partition? So we will get the sub intervals I1 as, sorry, this is 1.5, 1.5. So 1 to 1.5, I2 is 1.5 to 2, I3 is 2 to 2.5, and I4 is 2.5 to 3. Clear? That this is x0, x1, x2, x3 and x4. Clear? Clear? Okay. Okay. But suppose we had taken a partition, let's say P1 as 1.5, 2, 2.5 and 3. This would not be a partition. This would not be a partition because it is not starting with the starting element of the given interval. Clear? So make sure the set you are taking is a partition and obeys all the conditions a partition must obey. Clear? Okay. So next important term related to partition is what is the norm of a partition. What is the norm of a partition? What is the norm of a partition? So basically, suppose we have an interval I equals to a finite closed interval a comma b, and we take a partition as a equals to x0, x1, x2 till xn equals to b. Okay, and so this we can this partition can be used to break this interval into n sub intervals of the form xr minus 1 to xr for 1 greater than equals to r, sorry, 1 less than equals to r less than equals to n. Clear? Clear? Now see, this particular sub interval has some length, right? What is the length given? So we use this symbol delta r. It is simply xr minus 1. This is the length of the sub interval, right? This is the length of the sub interval. Clear? Clear? Norm of a partition is given by the maximum of all the lengths of the sub interval which a partition has created, right? So basically norm of P is given as the maximum of all delta r possible for r equals to 1 to n. Clear? I mean by it is that, see, you have taken a partition and the partition has given you n sub intervals. So every sub interval has a definite length. It is not mandatory that the lengths will be equal. The lengths of each sub interval is not mandatory to be equal. Lengths of each sub interval is not mandatory to be equal. So every sub interval which the partition has helped to create has a definite length, right? So the maximum of all those lengths possible from the sub intervals is given as the norm of the partition. Clear? Is given as the norm of the partition. For example, let us take a partition. Say we take an interval I 1 to 5 and we take a partition. We take two partitions to examine properly. So we take two partitions, P1 as 1 1.5, 2 2.5, 3 3.5, 4 4.5 and 5. Clear? And we take another partition, let's say 1 1.5, 2 3 5. Clear? Clear? Got it? Now in the case of P1, for P1 we can easily find out that every subinterval which this partition can create, the length of all those subintervals will be 0.5, right? Will be 0.5 for all 1 less than equals to or less than equals to n, right? Clear? So that means the norm of P is simply 0.5. Okay, not much work to do. But in case of P2, what are the subintervals which we can find? So the first subinterval is 1 to 1.5. The second subinterval is 1.5 to 2. The third subinterval is 2 to 3. And the fourth subinterval is 3 to 5. Right. So respectively, what is delta 1? 0.5. What is delta 2? 0.5. What is delta 3? 1. What is delta 4? 2. So what is the maximum of all these lengths? 2. So what does that mean? The norm of partition P2, that means basically the norm of partition P2 is 2. Is it clear? Is it clear? Okay. The next concept which we are going to learn is refinement of a partition. What is the refinement of a partition? What do we mean by the refinement of a partition? Okay. What do we mean by the refinement of a partition? So in very simple terms, suppose you have an interval given a comma b, and you take a partition P as a equals to x0, x1 and so on till xn equals to b. Clear? Now you take one more partition P star such that it contains all the points which P has, but some more points other than the elements in P. Okay. Suppose you have something called, eta and eta star, say, and the other elements till xn equals to b. Clear? Clear? Basically, P is contained in P star. Okay, P is contained in P star, and P star may have other points too, but it must obey the obey the condition for it to be a partition. That's mandatory. Clear? Clear? So in this case, P star is called the refined partition of P. P star is called the refined partition of P. Got it? For example, suppose you take the interval I 1 to 3 itself, and you take P as 1, 1.5, which we have already taken, right? 2, 2.5, 3, and you take another partition P star as 1, 1.5, 1.9, 2, 2.5, 3. Clear? So P star contains P and has some more point. So P star is the refinement of P. Is it clear? Is it clear? Got it? So this is the refinement of a partition. Clear? This is the refinement of a partition. Okay. Now there is something more under this concept of refinement, which is called the common refinement of partitions. Okay. So let's say you have some given interval I, okay, and you have taken two partitions. Let's say P1 and P2 are partitions of I. Then P star, which is given as the union of P1 and P2, is a common refinement of P1 and P2. Clear? Got it? Got it? Clear? Because P star will contain P1 as well, P star will contain P2 as well, and it may have more points. As simple as that. Got it? So these were concepts of partitions. Now the concept of partition leads us to something more, which we call the lower and upper sums. Okay, lower and upper sums. Okay. Let us see it. So suppose let me give the heading first. Lower and upper sums. Clear? 1 minute, guys. Okay, lower and upper sums. So now to define this, let's take an interval I is equals to closed finite interval a comma b, and let us take a partition P. A equals to x0, x1. My whiteboard is lagging a bit, so please guys cooperate. x1, x2 till you have xn equals to b. Clear? So for this partition, for this given interval, we can take a subinterval IR as xr minus 1 to xr closed interval, and for this given subinterval it has a definite length delta r as xr minus 1, and this is for all r between 1 and n. Right? Now we define some more terms, that is small mr is given as the greatest lower bound of IR. Capital MR is given as the least upper bound of IR. Okay. Small m gives us the greatest lower bound of the complete interval I, and capital M gives us the least upper bound of the complete interval I, greatest lower bound of the complete interval and least upper bound of the complete interval I. And from these it is clearly evident that m of mr is clearly less, sorry 1 minute, and from these it is clearly evident that m is less than equals to mr, which is less than equals to capital MR, which is less than equals to capital M. Okay? Clear? Now what is the lower sum? Let's see. So for some given interval I, for some given function f and a corresponding partition P, the lower sum is defined as L of f, that is the function which we are given to find the area of, with respect to some partition P, is given as the summation r equals to 1 to n mr into delta r. Clear? mr into delta r. Got it? And in a similar way, the upper sum, which is u fp, is defined as summation r equals to 1 to n capital MR times delta r. Clear? Clear? Got it? Clear? One more thing, it is very much clear that what is the summation r equals to 1 to n of delta r? It is simply the sum of all the lengths of the subintervals, which will eventually give you the length of the complete interval, which is b minus a. Right? Clear? Clear? Let us define one more term for this interval, for this lecture, which is what we call as oscillatory sum. Oscillatory sum. Okay. So you are given a function f in an interval I is equals to a comma b, and for this interval you are given a partition P, and for this partition you can define the lower bound, the lower sum, as summation r equals to 1 to n, the GLB of some particular subinterval IR times its length, and UFP as, I have just written it, okay, which is given as summation r equals to 1 to n capital MR times delta r, right. If you subtract these two, UFP minus LFP, you get summation MR minus small mr times delta r equals to 1 to n, and this is called the oscillatory sum of f on I with respect to partition P, and is denoted as omega fp. Clear? Got it? Okay. So let this lecture be up till this much, guys. In the next lecture we will be talking about certain theorems related to these upper sums and lower sums. Got it? So meet you guys in the next lecture.